I'm Jeff Groh, and this is Partial Differential Equations. Today we're going to talk about cylindrical coordinates, in R3. This is a next logical progression after studying polar coordinates in R2 because we don't get a lot of new analysis in this subject. It's very similar to what we've already seen. We're going to look at steady state temperature in a cylinder. So we'll be looking at the Laplacian equal to 0, and in cylindrical coordinates that'll be two derivatives with respect to r on u, 1 over r times the derivative of u with respect to r, plus u, z, z. The boundary conditions that we are going to impose, let's suppose we have z equals 0 here and z equals h for the height of the cylinder. This cylinder will have a radius a. The boundary conditions will be u at r z equals 0 will be 0. U at a comma z equals 0. And on the top, u of r h equals u bar of r. So we'll have potentially non-zero boundary data on the top disk, but on the sides and on the bottom disk, we'll assume that the data are identically 0. We will begin, of course, with a separability assumption, where we can separate u as a product of functions, one involving only the radius r and the height z. Plugging this into our partial differential equation, we get r prime prime z, 1 over r, r prime z, and then r z prime prime. Dividing through by rz, we can see that this will be pretty easy to separate. We'll move this term to the other side. We'll get negative z prime prime over z equals r prime prime over r plus 1 over r, r prime over r. So the question is the constant that we set this equal to going to be positive, negative, or 0? Remember, by trichotomy, those are the only three options for real numbers. So we'll set this equal to some constant k, and we'll try to decide which is it, 0, positive, or negative. You can see then that if k is equal to 0, then we'll have r prime prime plus 1 over r, r prime equals 0. And if we move this term to the other side and divide by r prime, we'll have r prime prime over r prime is minus 1 over r. Integrating, we'll have the log of r prime is equal to minus the log of r plus some constant of integration. So exponentiating r prime will be some constant divided by r, and then we integrate again. R is a constant times the natural log of r plus some other constant. You can see that this has a singularity at r equals 0 and hence is thrown out on physical grounds. If k is positive, we might set k equal to lambda squared. We'll have the following equation, r prime prime plus 1 over r prime minus lambda squared r. And we get something called a equals 0. And we get something that is called a modified Bessel's, modified because of the negative here, modified Bessel's equation of order 0. Modified parametric because of the lambda squared. And it turns out that the modified Bessel's equation of order 0 has two solutions, one of which is going to be called k0, and the other one is going to be called I0. And k0 is thrown out on physical grounds because of the singularity at the origin. I0 is also thrown out because we require that at r equals 0 on the lower surface to have a value of u equal to 0, which will never happen here. So both of these are thrown out on physical grounds. So by trichotomy, we're left with k is less than 0. We'll set k equal to minus lambda squared, and that will give us r double prime plus 1 over r prime plus lambda squared r equals 0. And we have here a parametric form of Bessel's equation of order 0. This is good news because we already know the solution. We'll have a bunch of solutions of the form r equals j0 of alpha 0n over a r. We also had the differential equation negative z double prime over z equals negative lambda squared. So we knock the negative off of both sides. And we can find that a general solution for this is c1 hyperbolic cosine of lambda z plus c2 hyperbolic sine lambda z. Now on the lower surface at z equals 0, we have to have a value of 0 here. And when you evaluate this at z equals 0, you get c1. And so c1 must in fact be 0, and our solution can only have hyperbolic sines. We have then the general solution and the only thing left to do is to determine how the coefficients a sub n depend upon the data on the top disk. To do this, we'll note that u bar is what you should get when you evaluate this solution at z equals h. Using a weighted inner product, as before, with a basis element you can see that we'll get this. And just let me make a note that this is the weighted inner product, whereby we have to multiply by an extra factor of r before we integrate from 0 to a. We can solve this equation then for the coefficients a sub n, and that gives us the complete solution to the problem of heat on a cylinder where we have 0 data on the bottom and on the sides, but not 0 data on the top disk. What happens when you have a cylinder and we're dealing with steady state heat with non-zero data on the lateral surface? In this case, we end up with the constant k being greater than 0. Our solution ends up of the form we end up with a modified Bessel's function with order 0. So we end up with these I naughts. And also, we'll end up with the sine function instead of the hyperbolic sine in this case. Because of the 2 pi periodicity, we're going to have n pi over h times z. The coefficients in this case will be 2 pi over I naught of n pi a over h. H, the integral from 0 to h of our boundary data will be of the form u bar of z. This inner product will be times sine of n pi over h z. We'll next turn to the Helmholtz equation. On a disk. Since we're on a disk, r will be between 0 and a, and theta, of course, will take values between 0 and 2 pi. We'll have to assume 2 pi periodicity. So every 2 pi, we repeat what happens at 0. The same is going to have to be true for the partial derivative with respect to r. We will assume, of course, that u is r times some theta, and plugging this into our differential equation, we'll have r prime prime theta plus 1 over r prime theta plus 1 over r squared r theta prime prime equals minus k times r theta. We will, of course, divide everything in sight by r theta. We'll have r prime prime over r plus 1 over r, r prime over r, plus 1 over r squared theta prime prime over theta equals minus k. At this point, we need to move a couple terms around. R prime prime over r plus 1 over r, r prime over r, plus k equals minus 1 over r squared theta prime prime over theta. To completely separate the variables, we have to multiply through by r squared. At this point, we can set the right-hand side equal to some constant lambda. By trichotomy, we have to check the three different possibilities. Is lambda 0? Is lambda negative? Is lambda positive? It's pretty easy to see that lambda equals 0 is out, because in that case, there's no way to get 2 pi periodicity. The same is true with lambda less than 0. It follows then that lambda will be greater than 0, and that will give you solutions theta equals c1 cosine of the square root of lambda theta plus c2 sine of square root of lambda theta. In order to get 2 pi periodicity, then, we have to have lambda equals m squared, where m is an element of the set of natural numbers, or potentially even the collection of integers, though putting in integers won't give you anything new because it's m squared. We have then theta is c1 cosine of m theta plus c2 sine of m theta. The only question that remains is, what do you get for r? For r, it's pretty easy to see that you get the parametric form of Bessel's equation of order m. So the solutions there are going to be Jm alpha mn over a r. We have then eigenvalues and corresponding eigenvectors. We'll get two linearly independent eigenvectors in each of these spaces corresponding to the eigenvalues lambda equals alpha mn over a squared. Those are Jm alpha mn over a r times the cosine of m theta and Jm alpha mn over a r times the sine of m theta. We next turn to Poisson's equation on a disk. So Poisson's equation is some function f is equal to the Laplacian of u. So we have a non-homogeneous problem. The classical way to solve this is to break this into two problems. We'll get the general homogeneous solution, and we'll get a particular solution to the non-homogeneous problem. We'll combine those together to get the general solution to be the sum of the two. We must also assume certain boundary data. We need this function u bar to be 2 pi periodic. And the way that we're going to break this down On the homogeneous problem, that's where we'll have our data. For the particular solution, we'll assume that the boundary data is identically 0. For the steady state problem, this is done. We've already solved the steady state problem on a disk. For the second problem, we use something called the method of Eigenfunction expansion. We'll assume that U can be expressed where m goes from 0, n goes from 1, in the form amn cosine of m theta plus bmn sine of n theta as a linear combination of these eigenvectors. One question to ask is, does this satisfy the boundary data? The answer is yes, because when you evaluate this Bessel's function at a, you're evaluating then at a root, and so you get 0. It turns out we'll have the inner product of the function f with terms of the form jm alpha mn over ar cosine of m theta. A word about the integral. It's going to be a double integral because you have two distinct variables. R will go from 0 to a, and theta will go from 0 to 2 pi. The area element will, of course, be r times dr d theta, giving you that weight r automatically. We'll have to normalize this by multiplying by jm times your cosine, jm times your cosine. And this ends up giving you a value of -2 divided by pi alpha mn squared j m plus 1 squared evaluated at alpha mn times the integral from 0 to a, the integral from 0 to 2 pi, our function f times our Bessel's function times the cosine of m theta r dr d theta. The BMNs are very similar. We'll declare that to be relatively obvious. The only difference, of course, being that you end up with a sign in this location. Those coefficients worked for m greater than or equal to 1, so the only question is, what happens when m equals 0? What is a 0 in? And the only difference here is that you end up with a -1 over all this stuff, integral. And because you're using m equals 0, cosine of 0 is 1, and so you'll just have f times your jm, m being 0. B0n, on the other hand, since you'll be dealing with an m equals 0, will be identically 0. We'll look at a quick example about the simplest example you can have. In this case, you can see that the homogeneous solution will be identically 0. And then the question is, what happens with the particular solution using the method of eigenfunction expansions? We can then determine from our last example by substituting f equals 1 to figure out all of the coefficients. As you can see, our particular solution must be independent of theta, which means that our solutions will give us 0 when m is bigger than or equal to 1. So then we turn only to a0n, since b0n is already known to be identically 0. Negative 2 over alpha 0 n squared, j1 squared of alpha 0 n, you can see that the 2 comes from the integral from 0 to 2 pi being just 2 pi. That's where the 2 comes from, and it cancels the pi that was in the denominator. So we'll have j0 of alpha 0n over a r times r dr. And this will then give us a complete solution to the problem. We'll have a sum as n goes from 1 to infinity. These will be these coefficients, and the rest is pretty easy to see.